I just want to first of all welcome you to the meeting today, the London Foundations Connection. Before we get started, I want to go through a few practical things and then tell you a little bit about the reasons why we organised this meeting in the first place. So for the practical issues, my name is Matt Leifer, I'm one of the organisers. My co-organiser is sitting over there, Adam Cortland. So if anybody has any questions or issues, problems with the meeting today, then please talk to one of us and we'll do our best to help you out. You should have all picked up the name badge and the program. These are available on the desk out there in the dressing room. And so if you haven't picked them up, then they'll be there all day. So all the talks are going to be in here today, and the coffee breaks and lunch will be served in the room over there where you were in for registration. Okay, so now let me bore you a little bit with some background to this meeting. So quantum foundations as a subject is a very old subject. It goes back to the inception of quantum theory itself. People have always debated the foundations and interpretation of the theory. However, it's not always been the most popular subject to do research on, particularly within physics departments. Now, that attitude seems to be beginning to change slowly over time, partly due to the rise of quantum information science, partly due to interest from people in quantum gravity, changes to the funding landscape, and a variety of other reasons. What that means is that I think it's fairly safe to say that now there are more PhD opportunities, postdoctoral positions, and even in some cases faculty positions in this subject than there have ever been before. And that raises its own challenges, because what we would like to do, and what I would like to do in particular, is for the people who are coming through the London university system, I'd like them to have the best possible opportunities for those careers. To be a researcher in quantum foundations, you need to be a fairly independent thinker, and you need to have quite a diverse background. It's not just a matter of learning one approach to quantum theory, it's a matter of learning about mathematical foundations, about philosophical foundations, and a whole variety of different approaches. And it can be quite difficult to obtain that knowledge. So within London itself, we have quite a lot of activity in this field. If you take all of the colleges of London together, and then we have people in philosophy departments, physics departments, and mathematics departments across the capital, all studying different aspects of the foundations of quantum theory. But it's kind of scattered in that, in most cases, it's one or two people working in a department, kind of on their own sort of approach. So in my view, and the reason why I thought to organise this meeting, it would be good if people in London who work on this area, for some purposes, could act more like a single research group. Now, not necessarily for all purposes. I'm under no illusions that people who work on diametrically opposed approaches to quantum theory are going to start collaborating tomorrow. But in particular, from the point of view of people who are in the early career, getting the background and knowledge that they need to be successful in this subject, I think we would do better doing that together than apart. So this meeting is really my first attempt at organising something like that. So I hope people will find it valuable and useful. And if they do, I hope people will be keen to organise more of these meetings in the future. There are also other possible things that could be done under the London Foundations Connection banner. I mean, one could think about seminar series and online resources, mailing lists, and that sort of thing. So if anybody is interested in any of that, then I would love to discuss it with you at some point today. The final thing I should note is that when we were organising this meeting, we got a lot of interest from people outside of London, and indeed many people from outside of London are here today, and that's great. And what that indicates to me is that there's a desire for these sorts of activities also at the national level, so that's something that probably needs to be thought about as well. Okay, so moving on to what's going to happen today. in the morning session, we're going to have 2 tutorial lectures which will give overviews of 2 areas in the foundations of quantum theory. In the afternoon, we're going to have shorter research talks. So without further ado, let me introduce the first tutorial talk, which is from Hugh Jones from Imperial College. And he's going to give us an overview of PT-symmetric quantum theory.
Thank you, Matt, and thank you for inviting me here. Good morning, everybody. Okay, so this is my title. I'm going to give you an overview of PT quantum mechanics. This is a subject which has had a lot of activity in the last 10 years or 12 years, and been a big development in it. Whether it actually, in the end, contributes to the foundations of quantum mechanics is another matter, and I'll leave you to judge that. But I'll give you the story of what happened and where it's got to at this point. So this is my outline. The first main chapter will be on PT symmetry and quantum mechanics with various subheadings. I'll explain this as I go along. So there are altogether 7 different things in PT quantum mechanics. If I have time, which I may not, or I'll just go through very, very quickly, there's been a recent development where these ideas of PT quantum mechanics have been applied instead in a completely different field, which is classical optics, because it turns out in certain approximations you get the identical equation with different meanings to all the symbols in optics, and the ideas that have been developed in PT quantum mechanics can then be applied with very great interest, actually, in optics. So that's what I'll give you a very quick overview of that thing, I think, at the end. All right, so as far as PT quantum mechanics is concerned, so it all started with this this Hamiltonian here, which is p squared plus m squared x squared plus an ix cubed. So it's got the potential is actually not real, so that Hamiltonian is not Hermitian, but it is actually PT symmetric, and PT symmetry, P will take x to minus x, T, among other things, is an antilinear operator, so it takes I to minus I. So if you combine those 2 things, and Ix goes to Ix. So it's this Hamiltonian, while not Emission, is symmetric under PT symmetry. And it turns out, I mean, numerically and all kinds of other reasons now, that all the eigenvalues of that Hamiltonian, that non-Hermitian Hamiltonian, are actually real and positive. So that was a big surprise way back in about 1998. Actually, in a way, it's not completely surprising, because if you look at this in perturbation theory, you get indications why the energy levels should be real. The first order change to the energy levels is the expectation value of V, and that's 0. So that's okay. And then the second one is this well-known expression, and that's real. And you'll keep on going like that. You'll find that the odd ones are 0 and the even ones are real. And so in perturbation theory, you will get a real eigenvalue. But of course that doesn't prove the case, because you don't know if the theory converges, and probably doesn't. So that's only an indication. It's not proved by any means. But an actual proof of this property took quite a long time to come. And it was given eventually in this paper by Dory, Dunning and Tateo in 2001, so 3 years later, and it's a very, very complicated proof involving a lot of fancy mathematics, and exploiting the ordinary differential equations and the integral model of correspondence. So but anyway, it's rigorously proved now. Now, let's go through the usual argument, why we like Hermeticity. And one reason is that it guarantees you a real spectrum, and the way that works is the standard textbook thing. You look at the Schrodinger Equation, and then you sandwich it with the bra on the left, and because H is Emission, this thing is real, and that therefore this mod psi squared is real and positive, and therefore your E is real, has to be real. Or in terms of the wave function, if we do this argument in terms of wave functions rather than states, you get the equation E minus E star times integral psi star psi dx is 0, and that implies that E is real because, i.e. E equals E star, because psi star psi is positive definite. So that's the well-known argument. Now, if you try to do the same thing with the PT symmetric Hamiltonian, what happens then? Well, so now we don't have V star equals V, we have V star equals V of minus x. And so the corresponding equation to what we had at the bottom of the last slide is E minus E star times this integral, not psi star psi, but psi star of minus x times psi equals 0. Now, however, you can't make a rigorous conclusion that this equation implies E equals E star, because it could possibly be that this last factor could be 0. In the other case, it couldn't be 0, it was positive definite, but now this could possibly be 0. In fact, that does happen, that can happen. And we have to talk about PT can be broken or not broken, and it's broken when the wave functions do not obey the symmetry of the Hamiltonian, do not follow the symmetry of the Hamiltonian. That's because there's an anti-linear symmetry, it's not a linear symmetry. So that actually can happen. So it's, PT symmetry does not guarantee you a real spectrum, only if the PT symmetry is not broken. Now, this is the famous graph from the paper by Bender and co. And it shows the spectrum of this whole class of Hamiltonians, p squared minus ix to the n, which they regarded as a continuation in n, in the index n, from the harmonic oscillator. If you take n equals 2, you get p squared plus x squared harmonic oscillator, and then you just continue in this n. And what you see here is, so there's the harmonic oscillator, and what you see is that as you vary n, nothing much happens. Well, on the right-hand side, anyway, nothing much happens. These eigenvalues just kind of change smoothly, and nothing happens. And so that they're all real here, and they all continue to be real as you go as you continue in n. And in fact, that was the main. Originally, that was the main focus of the thing. That you concentrate on this side of the thing where everything is real and everything's fine. On the other hand, if you look to the left of this line of the n equals 2, if you continue backwards, what you see here, and which has become more important lately, is that actually this is no longer true, because, for example, here you've got two eigenvalues which have come together. So I'm showing the real part of the energy, and at that point they go into two complex conjugate pair. So that's where the PT symmetry is broken, and we don't have real eigenvalues anymore. We have a PT. And that happens, there's a whole accumulation of these things going on. So immediately you get less than 2, you will have some complex conjugate eigenvalue, in infinite number actually. So this is the famous graph which led to a huge amount of research. Now let me go back to and explain that a bit, because it takes n, it's minus ix to the n, and n is increasing, that requires a bit of explanation, because if we go through n equals 2, as I said, is a harmonic oscillator, n equals 3 is the ix cubed, which is what I started with. But if you go to n equals 4, the potential you're talking about is actually minus x to the 4th. And anybody, originally would put their hands up in horror saying, this is ridiculous, what are you talking about? This is the potential which is unbounded below. How can you be even talking about it? And the answer is that it can make sense if the problem is not formulated x being along the real axis, but ventures into the complex plane. And that's the way that minus x to the 4th potential can make sense. So the way that works is you look at the Schrodinger equation, and you look at the behavior of the wave function for large x. And you can get it either from WKB, or, which is equivalent to looking for an asymptotic balance between this term and that term. And so psi goes like this particular exponential. And then you look at this exponential, you see where does it decay exponentially. I write x equals r e to the r theta, I'm going into the complex plane, and it decays exponentially when theta has a certain value. And these values, these give you rays, which are called anti-Stokes lines. And if you look at, so here is a particular Stokes wedge. So this is for n actually. This is actually for n greater than 4. What happens is that this is if you go to infinity along anywhere in this wedge, off to infinity, anywhere in this wedge or anywhere in that wedge, then the wave function will decay, and you have a well-founded eigenvalue problem. And this situation, what these wedges actually start off being symmetric about the real axis. So at n equals 2, you go right along the real axis. As n increases, these wedges come down, and they miss they hit the real axis precisely at n equals 4. It turns out. So as I said, the wedges do not include when n is greater than 4. The wedges do not include the real axis. So it's okay for n equals 3. What I just told you before, that's fine. You can stay on the real axis, no problem. But if you have n greater than 4, greater than or equal to 4, then you have to go into the complex plane. You have to propose the whole eigenvalue problem in the complex plane, which is a bit strange, but there you go. But let me just emphasize, this is something which we've been doing recently, actually, is that if instead you're talking about the Schrodinger equation on a finite interval, like a Sturm-Liouville problem, then that's a completely different story. So I just have the Schrodinger equation with that potential. It's, for example, ix cubed with psi vanishing at -1 and 1. Then the spectrum looks like this instead. And what you're seeing here is this again. Now you are getting PT symmetry breaking for n equals 3 on a finite interval, because what this is showing is you've got two eigenvalues here which come together. This is just this little thing sticking out is just it's just a continuation of the real part. They're actually two complex, they're complex conjugates, and it should really stop there if I'm plotting the real part. But that's the sort of, it's a completely different story when you're on a finite interval. And you can stay on it. There's nothing, because you're not going to infinity. You can stay on the real axis. There's no problem in finite. Yeah. Now, okay. So what we've seen so far is that if you have these PT-symmetric potentials, ix minus ix to the n, and you're prepared to go into the complex plane, then you have a completely real spectrum, and then you think, okay, that's great. But that's not, of course, that's not the whole story, because quantum mechanics is not just about energy eigenvalues, it's about a whole probabilistic framework. And if we're talking about non-broken PT symmetry, then the natural orthogonality relation is not the conventional one where psi star chi is 0 for different eigenfunctions. Instead, it's always this psi star minus x that comes in. So that's the wave functions are orthogonal that way in the PT quantum as opposed to the standard way. And the problem is that, so that's the overlap of two different wave functions, but if you then take the wave function itself, that's the PT norm, is that, and that is now not positive definite. So if you wanted to have probabilities and have a probabilistic interpretation, you are in trouble, because that is not positive definite. So have we lost probabilistic interpretation in PT quantum? Because it's just a mathematical game. And the answer is no. It is possible to get around that problem. And the solution to that problem is to introduce, if you're going to do the PT quantum, you have to introduce a new scalar product in your Hilbert space. And that's due to Daniel and myself and Brody in 2002. So if PT is unbroken, you actually can choose the phase such that that is true, and then introduce this operator, C. It's sort of like a charge conjugation operator. It's not quite suggestive, which is just the sum over all your eigenvalues, psi, psi, not psi star psi, but psi, psi. And it turns out this operator, the C operator, has various properties. C squared is 1. C commutes with H and with PT. But the reason it's important, I mean, why we introduced it, is it's actually a grading operator. And see, what happens is that PT overlap actually alternates in sign if you go up on the energy levels. It's plus minus, plus minus, plus minus. And this C operator, if you multiply C times one of the eigenvalues, it actually changes the sign for the odd one. So it actually undoes the wrong sign of the odd eigenvalues. So that is then, you're now turning the whole thing into a positive definite metric. Before you did that, when we had the states which were some of which had positive norms, some which had negative norms, that's called a Krein space, and this is called a grading operator in a Krein space, which kind of makes things okay again. Now, so as I said, the previous scalar, the scalar product we had before which was this one, is actually you take the PT conjugate of psi and then integrate it with respect to chi. But now what we're saying is that let's now actually do another scalar product where we stick in this C in front of here. And what that does, as I've been intimating, it's positive, it's time independent, and it's independent of the path in the complex. If you integrate this in the complex plane, it's actually independent of the path. So this is great. We've constructed a new metric, and everything's right. Then you get positive definite probabilities and so on and so forth. But that's not free of cost, because the disadvantage is that it depends on the dynamics. It depends on the Hamiltonian. It's not the same for each different Hamiltonian has its own C. So whereas in ordinary quantum mechanics, the scalar product is just given to you once and for all. In PT quantum, because you have to, for each particular case, you have to go away and construct the metric. And in fact, you need, in principle, to construct C, you need to know all the eigenfunctions, which is a bit of a tall order. However, one can have approximations to that, of course. I mean, mostly we do perturbation theory, and you can calculate C in perturbation theory. And to do that, it's useful to recast the whole thing in an algebraic way. And it turns out also to be useful to introduce the Q operator. So we write C as e to the Q times P. And the reason for that is that two of these conditions here, this one and that one, are automatic. You can satisfy them automatically just by these symmetry properties of Q. If you make Q be odd in X and even in P. No, even in X and even in P. So that's satisfied two of the conditions that C has to satisfy, and there's only one left, which is that it has to commute with the Hamiltonian. So that's where. Now this depends on the particular Hamiltonian we're talking about. And so now I'm writing C as e to the QP, so that's that condition. Multiplied by e to the minus Q, I get that. Multiplied by P on the right, I get that. And PHP is actually H dagger, because P changes X to minus X, and that's the same as changing I to minus I, so this gives you the H dagger. So this is the condition, and this is called pseudo-Hermeticity. So instead of H dagger being H dagger, I mean H dagger is not equal to H, but we have to find this operator Q, which says that H dagger is e to the minus Q, H e to the Q. So this Q operator is completely central to the whole business. So is that clear? Any questions? So we have, instead of Hermeticity, we have pseudo-Hermeticity, and with respect to this Q, which we still got to find. But in fact, this relation here gives you, I mean, that's an algebraic relation which you have to solve for Q, so that's how you find Q, in perturbation theory in particular. But sometimes you can calculate it. Okay. So that, as I said, that's called quasi-Hermeticity. And another notation which was introduced somewhat around the same time by Mr. Vazada is just calls it eta. So eta is rated to RQ by eta equals e to the minus Q. And so that relation I just had on the previous page, if I write that in terms of eta, it just says H dagger is eta H e to the minus 1. And so H is quasi-Hermitian with respect to eta. And actually Q and eta are both Hermitian. That can be chosen, so. Right. Now, the new scalar product, which I mentioned, so where I stick in the C, can be written. Let me not go through the details of this, but you can bring it down to the fact that it's actually psi with the eta stuck in between. So so we've introduced a metric. So that instead of just being psi chi, the metric which is positive definite is psi eta chi. And also, q is supposed to be positive definite in emission, so we can actually introduce the square root of it, which is e to the minus a half q. And then it turns out this is what Mustafa realized, is that given this eta, you can take the square root, and then if you construct this little object, little h, which is rho h to the rho to the minus 1, which is the same as e to the minus a half q, h e to the half q, then this little h is Hermitian. It's actually ordinarily Hermitian. And the proof of that is quite simple. You start from, this was the defining relation, this is the pseudo-Hermeticity one, multiplied by e to the half q on the left, and e to the minus a half q on the right, and that results in this equation. And this was my definition of h. I said this was h, and this on the left-hand side is actually h dagger. So this equation, this equation and that equation are completely equivalent. And so what it actually says, what this really says is that, so I said there's an h here, which I can define, which is a similarity transformation on my PT symmetric h. And that h is Hermitian in the ordinary sense. So what this says is that actually a quasi-Hermitian system is equivalent to a Hermitian system under a similarity transformation. And the crucial thing is the similarity is not a unitary transformation, it's a similarity transformation. And that's the big difference. So, okay, so you might say, okay, well that's the end of it then. I'm just doing ordinary quantum mechanics in disguise, which to a certain extent I am. But the thing is that actually this little h, if you start with a nice simple big H like ix cubed, which I did, and you try to construct a little h, you'll find it's immensely complicated, and in fact even non-local as well. So you can formulate, problems could be formulated that they're simple in one picture and very complicated in the other. So let's talk a little bit more about that similarity transformation. So I want psi to generically to be the states and big A the operators of the H system, and little phi the states and little a the operators of the equivalent emission system. Sorry, so I should say obviously since they're equivalent, all the eigenvalues the eigenvalues of each system are identical. And that's okay. So this is the complete similarity transformation. The states get multiplied by e to the half q, and the operators get e to the half q, e to the minus half q on the other side. And then if you calculate the overlap, the usual overlap in the Hermitian system, and translate it into the pseudo-Hermitian system or the PT system, then you get this that the usual overlap here translates into the overlap of the corresponding operator here, but with this metric included. And if A is Emission, if we're talking about observable in the corresponding Emission system, then your corresponding operator A is quasi-Emission, as was H. H was the first example, so A dagger also satisfies that, and that's an observable with real eigenvalues, because it inherits the real eigenvalues from the Emission system. Now, I've spoken a little bit about this equivalent Hermitian Hamiltonian, and I just want to show you very briefly how you would go about it using these commutation relations which you've got to solve. So we have to solve this equation. And we're talking about the Hamiltonian where H0 is Hermitian and the interaction is non-Hermitian, which is very, very typical of what we're doing. Or anti-Emission. So we do an expansion, we're doing a perturbative expansion of Q, and expand this whole relation in powers of G. And what you get is a whole infinite series of commutation relations to be solved. So the Q1 operator is found by finding that operator, which when commuting with H0 gives minus 2H1. And then now you know Q1, then H0 with Q3. Q3 is given by this one, and Q5 is given by that, and so on and so forth. And similarly, the little h, the equivalent emission Hamiltonian, the isospectral emission Hamiltonian, is an expansion, and you find that the H0 is a H0, obviously. Then the H2 is given by the commutator of the Q1 with H1. The H4 is given by Q3 H1 and this triple commutator, and so on and so forth. And actually, the odd ones vanish, H1 and what can be chosen to vanish. So if you try and apply that, let's see what happens if we apply that process to this Hamiltonian with the Ix cubed potential. Actually, you have to, in this case, you have to stick it. To do perturbation theory, you have to have an x squared in it to start with. You can't do the massless case. You need a harmonic oscillator as your H0 to start off with. Anyway, so the equations, solving the above equations, you get, this is what Q1 looks like. And then Q3 looks like that, where and these S's, which crop up, are fully symmetrized polynomials of degree x to the n, p to the n. And we carried this calculation up to order q to the 9th, so it gets very, very messy. And then you go and calculate the h, the contributions to the emission Hamiltonian. And this is what the first non-vanishing contribution looks like this. H2 is x to the 4th. And it also involves, which is fine, but then it involves this S22, and S22 is this object. So what we can see from that is that this H2, which is already fairly complicated compared with the H that we started from, it contains a term in plus x to the 4th, which is a nice Hermitian potential, but it also contains these momentum-dependent, or i.e. derivative terms from this S22. So even to this order, the equivalent emission Hamiltonian is momentum-dependent Hamiltonian. And if you go to order x to the 4th, g to the 4th, it gets worse. You have a minus x to the 6th, you have a p to the 6th term, and you have all these terms here. So that's very, very complicated, and you can see what would happen if you summed it to all orders. All these derivatives would actually tell you you're discussing a non-local theory. So the equivalent of Hamiltonian to the simple Ix cubed is actually a non-local emission Hamiltonian. And that's generically the case. That's generically the case. There's one Hamiltonian. In fact, it's the most. In a way, it's the most. It's a kind of paradigm because it's the one where I started off with. Minus x to the 4th. What does that mean? We discussed all that. But it turns out that particular, and it's right on the border between when you have to go into the complex plane and when you don't. And it turns out in this case, actually, you can construct exactly the equivalent emission Hamiltonian. Well, as I said, we must go into the complex plane, so I'm going to change the notation and call this Z instead. So this is the Hamiltonian. Now I can discuss the n=0 case as well. That's the Hamiltonian I'm talking about. Now, that's in the complex plane, and I can do it on some curve which goes out to infinity within these Stokes wedges. And you've got a great freedom to choose which curve you go along. And so what we want to do is reformulate this as a problem for real x by parametrizing along some curve. But the question is which curve. We've got a whole infinite variety of curves to choose from, and in this paper we tried various curves and it didn't work. And then eventually we found this magic curve with which everything just falls out. And it turns out to be that's the curve, which is a hyperbola. It's this curve here. Which doesn't go, this is the center of the wedge, where it goes down purely exponentially. Here it goes down exponentially and oscillatory. That's okay, as long as it's got some exponential decay, that's fine. So, if you choose that parameterization, then you get a new Hamiltonian, which is that, which I call H sub x. This is the anti-commutator. And now this P is d by dx, not d by dz. So I want to find the equivalent Hermitian Hamiltonian to that. So I'm going to write it as h0 plus epsilon h1, where h1 is the emission part and h1 is the anti-emission part. I'm going to stick in an artificial epsilon in front of the anti-emission part, expand an epsilon, and then set epsilon equals 1. And the reason I can do that is that the expansion is going to terminate. So, in fact, the first equation we have to solve is this, q1 h0 is 2h1, and we have to solve that. Then you go ahead and calculate q3. That's given by the commutator of q1 with q1 with h. But q1 with h is a function of p. Q is a function of p, so that vanishes. And all the way down the line, all the right-hand sides of these things vanish. So in fact, that's it. Q1 is it. All the other ones are 0. Q is equal to Q1. And I can put epsilon equals 1, no problem. And then also the little h is known exactly, and this is what it comes out to be. It comes out, it looks like this. It's this funny Hamiltonian. It's got p to the 4th term, an x squared term, and a p term. Now, as I said, this doesn't look like a conventional Hamiltonian, but if you take a Fourier transform, and also as a slight rescaling, then it looks like the p to the 4th goes to y to the 4th, this becomes the p squared, and this becomes the y. So it's just a conventional anharmonic oscillator with a positive x to the 4th, and y to the 4th. So that, it turns out, that is the equivalent harmonic of this minus x to the 4th, which you go in the complex plane. Very, very interesting. And you can also do the same thing for m not equal to 0, and well, it's not a non-symmetric, an asymmetric potential, and if n is greater than that, it becomes a double well potential. So that's one case where you can actually construct absolutely specifically what the little h is, and it's local. Well, it's not local because it was actually in p space rather than x space. Now, okay, so we've discussed reality of eigenvectors, just introducing the new metric, and now the other thing you want to do always in quantum mechanics or quantum theory is calculate green functions. And so how do we do that? Well, there are 3 ways really. You can do the standard quantum mechanical calculation using the wave function, or you can treat quantum mechanics as a zero-dimensional or one-dimensional function integral. And then you can do various approximations to that functional integral, and that from the functional integral you get perturbation theory, strong coupling expansion, truncators of Schrodinger Dyson equation, and so on and so forth. So let me concentrate on these 1 and 2. So if you're calculating in quantum mechanics, in principle, what we should calculate the expectation value of an operator is we should always stick in the c to the minus q. We should always stick in the metric, and which you can, let's see, you can write it that way if you wish. Oh, I see. Sorry, this is psi, and if you turn it in terms of phi, it becomes phi naught, and then this transformed operator, phi naught. So the psi naught is a ground state wave function of the PT-symmetric Hamiltonian, and phi naught is the ground state wave function of the equivalent emission one. And you might at some point have to calculate this over a contour. But in fact, in one of the earlier papers on this game, Bender et al. Calculated the expectation value of x simply this way. They just integrated psi naught x psi naught, no star, just psi naught x psi naught, and that's what they got. And what I want to show you is that actually that is equivalent. It turns out that is equivalent to what I'm doing here, because we have this similarity transformation, psi naught is relative to phi naught by that, and we can choose psi naught to be real. So it's a question of what's the relationship between psi naught star and psi naught. And so psi naught star is e to the half q star phi naught. Q is pure imaginary and antisymmetric, so q star is minus the half q. Phi naught is that. Put these together, you get e to the minus q psi naught. So then psi naught is e to the q psi naught star. So the expression that Bender used, which is psi naught next to the n psi naught, is actually originally had an e to the minus q here, star, and you change it, sorry. That's right, so the first factor is this here, and then you either integrate by parts or you use the antisymmetry of P, you pull it through, and it changes sign, and so you get psi naught star e to the minus q. So this expression, which is what Bender originally used to calculate in perturbation theory, or whatever, is in fact equivalent to what I would say is the correct way of calculating a green function, which is that you calculate the expectation value including the metric. So that clears up one problem. The functional integral is sort of interesting because it turns out that the functional integral for that expectation value, the expectation value including the metric, is just the standard functional integral. And there's no mention of eta on the right-hand side. Eta just doesn't appear. So why is that? It's quite tricky, actually. The reason is that in the derivation of the functional integral, that comes from, ultimately, from the Heisenberg equations of motion. And when you go in PT quantum mechanics from the Schrodinger picture to the Heisenberg picture, you have to be very careful. So we have to look at that transformation from the Schrodinger picture to the Heisenberg picture. So we define the Schrodinger and Heisenberg by psi s, psi h, identify the states at t equals 0, then psi s is that and the bra is that. And you identify the Heisenberg operators, which h of t, which corresponds to the Schrodinger operator, by considering this object. Now, I'm doing that, I'll show you that that's correct. So you have to find the operators by considering that object. And then you rewrite it in terms of Heisenberg operators, and you find that psi s eta as psi is psi h eta e to the iht as of t e to the minus iht. So that says that the corresponding Heisenberg operator is this thing, which is the usual expression. So from now on, everything will go through. But in order to get that usual expression, you had to stick this eta in. Actually, sorry, I skipped over that too quickly. But what the crucial thing is actually here. You see, this was the psi h. There's the eta. And what's happened here is I've pulled the eta through the h dagger, and it turns it into an h. So if you didn't have it, you see, you'd have e to the ih dagger t as, which is something funny, and that wouldn't work. Nothing would work. So that eta is actually crucial. It pulls it through, turns out into an h. Now that actually goes because h is not emission. This is actually not. It's a similarity transform again. It's not a unitary transformation, but it preserves the canonical equations of motion. Equal time commutative relations, and gives a standard, the usual standard Heisenberg equation of motion. And I'll emphasize again, that only works if the matrix elements are calculated with the inclusion of eta. So, the functional integral and so on, they do implicitly involve the metric by the definition of what the Heisenberg operator is, but it doesn't appear explicitly. And then you can go away and calculate green functions just in the standard way with the functional integral. Without mentioning eta, without the need to calculate eta, which is very, very good, because eta, I'm sorry, eta is actually very, very complicated to calculate usually. But if you calculate things in the functional integral method, and methods that come from that, like perturbation theory, then you don't have to worry. So that's and that's also very good for the generalization of this to field theory. I mean, there's been some attempts to generalize this whole thing into field theory, and the same thing with field theory. It would be a disaster if you had to try and calculate the C operating field theory, but if you do it the functional integral way, you don't need to. Now, okay, so far I seem to manage to get over all these kind of various problems which should be presented, but in the final analysis, I think I'm actually here on false pretenses, because I don't think this is a replacement for ordinary quantum mechanics. It doesn't really have that much to say for the foundations of quantum mechanics, because it's okay. If these systems are treated as fundamental rather than as effective Hamiltonians, if you treat them as effective Hamiltonians, there's no problem whatsoever. If you want to treat them as fundamental quantum mechanical Hamiltonians, there is a problem. It's okay if they're treated in isolation, but if you try to interface those Hamiltonians with the rest of the world, which is Emission, then you run into severe problems. And that I think is the real sticking point of it. So there's two problems. One is scattering, and the other one is adding interacting in different ways with the Emission world. So if you talk about scattering in these non-Hermitian theories, well, in general, the standard unitarity is not conserved. And let's just do a very simple example. Let's consider a single complex delta function potential at the origin. That's actually not PT-symmetric, but it falls into the larger class introduced by Mr. Fazade of quasi-Hermitian systems. So there is a similarity transformation for it. So this thing here is supposed to represent a delta function, and so we have incoming wave, transmitted wave, reflected wave, and for example, that's the scattered probability is that expression, where Q is k over lambda, and that can be greater than 1. If epsilon is greater than 0, then that whole thing is greater than 1, which you may not like. I don't think you would like. So the question is, what can you do about that? Well, number one is what I just mentioned before, is you can treat the non-Hermitian Hamiltonian as an effective Hamiltonian. So we're talking about an open system, and for example, probability is leaking in from some part of the system which we haven't taken account of. That's one way of saying, treating this whole thing. Or you could try to stick to treating it as a fundamental Hamiltonian and try to patch things up using the similarity transformation. And if you try to do that, well, what you would try to do is actually use a different wave function, capital psi, which involves this rho, which is the square root of psi, instead of the usual wave function. But the problem is, and that will patch up unitarity. If you use that, you'll find out that the probability in that calculated that way would be considered. So you patch up unitarity, but the problem is that it's actually this is a non-local transformation, and what it does, it completely changes the actual picture. See, the picture was we have waves coming in from infinity and going out to infinity again, coming in from infinity on the left, and with only an outgoing wave to infinity on the right. But if this new psi of x actually contains both on the right, both outgoing and incoming waves, so you completely change the whole picture. What are you talking about? This isn't the conventional scattering things coming in from the left and then being transmitted or reflected. You've got waves coming in from both sides. So it's just a very different picture. You don't really know what you're talking about. So that's one very big problem, which I don't think there's any solution to that, personally. And then the other thing is the following: that okay, we're very proud of having, in most cases, this real spectrum. But what happens if you try and couple that? We have a little weak coupling of that isolated non-emission system and try to couple it to an emission system. So here's a very, very simple example. I've got a harmonic oscillator, emission harmonic oscillator, real eigenvalues. I couple it to the most simple thing, shifted harmonic oscillators. All I've done is shifted y by a bit, by I. And but that's a non-Hermitian Hamiltonian, which by itself would have real eigenvalues. And then I couple them with the gxy.